Hello dear students, welcome you all for transmission and distribution class. So continue with the performance of the transmission line. We are in the short circuit lines now. In the previous classes we have seen how a short transmission line is analyzed with the three phase and single phase, and we have seen some problems also. Now we will see what is the effect of load on load power factor on regulation and efficiency. So the regulation and efficiency of the transmission line is depend upon considerable extent upon the power factor of the load. So effect of the regulation we will see. The expression for the voltage regulation of a short transmission line is given by a percentage regulation is equal to IR cos phi r plus IXL sin phi r divided by VR into 100 with a lagging power factor. And if it is in a numerator, it will become minus if it is leading power factor, that is IR cos phi r minus IXL sin phi r. So the following conclusions can be drawn from the above expression is when the load power factor is lagging or unity is such leading that IR cos phi r is always greater than the IXL sin phi, then voltage regulation is positive. Receiving end voltage will be less than the sending end voltage. By seeing the equations only we can tell. For a given value of VR and I, the voltage regulation of the line increases with the decrease in the power factor of the lagging load. Obviously, as the power factor decreases, the regulation is increases. When the load power factor leading to this extent that IXL sin phi r is greater than the IR cos phi r, then the voltage regulation is negative. Then the receiving end voltage VR is more than the sending end voltages. So these things happens in the leading power factor cases only. Then for a given value of VR and I, the voltage regulation of the line decreases with the decreases of the power factor in the leading loads. Okay, so these things we can conclude that using the equations only. Now we will see effect of the transmission efficiency. So power delivered to the load depends upon the power factor. We are knowing that one. P is equal to VR I cos phi r, or you can write I is equal to P by VR cos phi r. Or in case of three phase, this is P is equal to VR 3 VR I cos phi r, or I is equal to P by 3 VR cos phi r. It is clear in each case that given amount of power transmitted and receiving end voltage VR and the power transmitted and the receiving end voltage VR and the load current I is inversely proportional to the load power factor cos phi r. Consequently, with the decrease in the load power factor, the load current and hence the losses are increased. This leads to a conclusion that transmission efficiency of a line decreases with the decreases in the load power factor. So as the power factor is good, that is unity, means obviously losses are less. If power factor is poorer, means very less values, like nearer to 0, that is 0.2, 0.3 and all, we are having more losses. So obviously the transmission efficiency decreases. Okay, so we will see some problems on this one, and after that we will move to the medium transmission line. So this is regarding the theory part of the short transmission line. We see one problem here, that what is the maximum length in kilometer for single phase transmission line having copper conductor of 0.775 cm square cross section over the 200 kilowatt at the unity power factor at 3300 volt are to be delivered. The efficiency of transmission is 90% and the specific resistance is 1.725 micro ohms centimeter. So given details you need to write down. Area of the conductor is given, that is 0.775 centimeter square. Receiving end power PR is given 200 kilowatt. Receiving end voltage is 3300 volts. Efficiency of the transmission line is 0.9, that is 90%. Specific resistance rho is given by 1.725 micro ohms centimeter. So we need to calculate resistance of the conductor, receiving end current and length of the transmission line. So as we know that R is equal to rho L by A, to find the value of L, initially we need to calculate the R value by obtaining the total line losses. So total line losses, how to calculate? Power sent minus power received. We are knowing losses is nothing but power sent minus power received. Or what is the power sent here? We don't know what is power sent, but we are knowing power received and efficiency. So we can write that power received by efficiency minus power received, or 200 kilowatt by 0.9 minus 200k, or 222.22 minus 200k. We will get 22.22 kilowatt as the losses. Once we know the losses, total losses is nothing but 2I square R. Okay, or 2I square R is the I square R is the losses. So here PR minus PS is equal to I square R. Or losses occurring at the face is I square R and neutral, because why 2 IR is two lines are there, because one face and one neutral, two lines togetherly we are taken, no. So in this loop we are consider it as 2 I square. Now to get the total line losses, we need to find R. R is equal to total line losses divided by 2 I square, or 22.2 K divided by 2 I square, or receiving end current I can be taken by PR. PR is equal to VRI cos phi R, or I is equal to PR by VR cos phi R. So considering the unity power factor here, we can get this I as 60.6 amps, and we will get the R as 3.025 ohms. So once we got the R as that one, we need to calculate the L using the equation R is equal to rho L by A. L is equal to rho A by A, RA by rho, or L is equal to, we will going to get 1.36 into 10 raised to 6 centimeters, which is nothing but 13.6 kilometers as the answer. Okay, this is one of the typical problem. They are given with the efficiencies and losses. Efficiency is given and the power cent is given. We need to calculate the length of the line. This is one typical problem. You can try by your own. We will see another problem now. Next problem is an overhead three-phase transmission line delivers 5000 kilowatt at 22 kilowatt at 0.8 power factor lagging. The resistance and reactance of the each conductor is 4 ohms and 6 ohms respectively. Determine sending end voltage, percentage regulation, and transmission efficiency. So write down what are the things given. Power factor is 0.8, receiving end power is 5000 kilowatt, VR, that is receiving end voltage is 22 kV, receiving end voltage phase we need to calculate, because it is a 3 phase, obviously 22 by root 3, that is 12.7 kilovolt. R is 4 ohms, XL is 6 ohms. We need to calculate what is I, what is VS, what is percentage regulation, and what is the efficiency. So impedance is given by R plus JXL, or that is 4 plus JX. If you want to convert it into the polar form, we will get 7.21 at an angle of 56.3. Or we are knowing that VR reference is equal to VR plus J0. We will write it in that form. Or we know that PR is equal to 3 VR I cos phi R, or I is equal to PR by 3 VR cos phi R. By putting all those values, we will get I is equal to 164 amps, and getting I is equal to I into cos phi R minus J sin phi R. So cos phi R given is 0.8 and sin phi R is 0.8. So we will get the current as 164 at an angle minus 36.86. So next is we need to find out the Vs. We are knowing that Vs is equal to VR plus Iz. This is the equation of the short transmission line. So writing all the values, actually VR we are written, and I just now we are calculated, and Z we are knowing by the R plus JXL. So after adding all these things, we will get the Vs as 13,820.63 at an angle of 1.631 volts. So this magnitude is 13,820 and the angle is 1.61. So if you want the line voltage, that is multiplied by root 3 to the 1, you will get 23,938 volts. So percentage regulation is given by Vs minus VR by VR. So here we are writing the phase voltages only, and that is 13,820 minus 12,700 divided by 12,700. We will get 8.82% as the voltage regulation. Total line losses is 3I square R, because the 3 phase I is 164, R is 4. We will get the 322.752 kilowatts as the losses. So power cent is power at receiving end plus total losses. It is 5000 plus 322. We will get 5322.752 kilowatt. So efficiency is given by PR by PS. We will get 93.93% as the efficiency. Okay. Next, one more problem is that it is a 3-phase 50 watt 16 kilometer long overhead line supplied 1000 kilowatt at 11 kV 0.8 power factor lagging. The line resistance is 0.03 ohms per phase per kilometer, and the line inductance is 0.7 millihenry per phase per kilometer. Calculate the sending end voltage, voltage regulation, and efficiency of the transmission. So this is also same thing. You can do by your own this problem. You take it as a assignment, and answers are given here. You solve it by your own. Okay, any of the problem is solved here. You solve the problem by your own. If you find any difficulties, you can ask me. Thank you.